Welcome to The Explainer. Today, we're jumping right into something absolutely mind-bending. We are tracking a massive evolutionary leap that connects the deep ocean directly to the cutting edge of space tech. Seriously, we're about to completely rethink how we talk to satellites, rovers, and even astronauts. So let's kick things off with a slightly weird question. Think about whales for a second. They returned to the ocean, about 50 million years ago, right? They evolved these amazing flippers and perfectly streamlined bodies. But why on earth do they still have to come up to the surface to breathe air? After all that time in the water, why didn't they just re-evolve gills? Well, Dr. Kang has a brilliant name for this. He calls it an evolutionary trap, or evolutionary path dependence. Basically, once a complex system, whether that's an animal's biology or human technology, starts down a specific path, it gets locked in. To reverse course would just cause massive disruption. You'd practically have to break the whole thing down. And Dr. Kang warns that if we build our massive future space infrastructure entirely on limited radio waves, we are walking right into this exact trap. We'll be stuck with a fatal flaw, constantly having to surface for air, just like the whale. And that biological quirk perfectly frames the crisis we're facing right now. Section 1, Evolution's Trap and Space Comms. Think about how real technological leaps happen. Look at China, for example. They pretty much entirely skipped the era of magnetic strip credit cards and all those clunky card-reading machines we built up in the West. Instead, they vaulted straight from cash to QR code mobile payments. Since they weren't bogged down by old legacy infrastructure, they could just grab the superior tech right out of the gate. And you know what? That is exactly what we need to do in space communication. We literally have to skip expanding our old radio systems and leap straight to lasers before we get completely locked in. So what's wrong with the old way? Section 2, the fatal limits of radio. Let's look at the huge bottlenecks with the tech we've relied on for decades. For starters, we have a massive, and I mean massive, scale problem. When you fire a radio wave through the vacuum of space, it spreads way out and loses a ton of energy over those huge distances. To catch those incredibly weak, exhausted signals back here on Earth, we have to build giant dish antennas. And I'm talking 70 meters across. That is practically the size of a football field. These colossal structures cost roughly $100 million a pop, just to catch a faint whisper from a spacecraft. But honestly, the giant hardware is just the tip of the iceberg. Because those radio waves spread out everywhere, the frequencies get incredibly congested. It's like a crowded room where everyone's shouting over each other. It also means the signals are super easy to intercept. If you're broadcasting a wide net, anyone with a decent antenna can just listen in. Plus, trying to sort out all this interference is a total bureaucratic nightmare. Getting international frequency approval can actually stall a multi-million-dollar satellite launch for an entire year. And to top it all off, the data transfer rates are just painfully slow. Speed is the real bottleneck here. Consider this. Voyager 1 back in 1977 communicated at 2 kilobits per second. Okay, sure, that was the 70s. But fast forward to the Mars Reconnaissance Orbiter in 2005, if you want to download a standard 4 terabyte hard drive of data from Mars using radio, it literally takes 2 agonizing years of continuous downloading. 2 years! Even the New Horizons probe took 15 long months just to send back 6 gigabytes of photos from Pluto. It's wild. Clearly, we need a better way. Section 3, Lasers, Space's Broadband. This is where we make our big evolutionary leap. When you put these two technologies side by side, it's almost not even a fair fight. Radio spreads wide, needs 70-meter antennas, is heavily regulated, and gets lots of interference. Lasers, on the other hand, use a highly focused beam of optical light. That means you only need a small 3 to 5 meter telescope on Earth to catch the signal. Because that beam is so tight, it doesn't cause interference, meaning you completely bypass that whole bureaucratic nightmare. And security? Oh, it's incredibly secure. To intercept a laser transmission, someone would literally have to fly their receiver directly into the 15-meter path of the beam. But the true magic, the absolute game changer here, is the speed. NASA recently ran a test called T-Bird, and they achieved a mind-blowing 200 gigabits per second from orbit. Let me put that speed into perspective, because the difference in scale is just staggering. That T-Bird module, it wasn't some massive dish. It weighed just 3 kilograms and was about 18 centimeters long. It's basically the size of a box of tissues. Yet this tissue box downloaded 4.8 terabytes of data in just 5 minutes. Remember that Mars orbiter we talked about? That exact same amount of data took 2 whole years over radio. A literal tissue box just out-downloaded a $100 million giant space dish in 5 minutes. Okay, as incredible as this sounds, it's not quite a walk in the park. Section 4, Hurdles lasers must overcome. The first massive physical hurdle is aiming. Think about it. A satellite in low Earth orbit is screaming through space at 7 kilometers per second. From that blindingly fast platform, it has to fire a microscopic laser beam and perfectly hit a ground telescope that's only about 50 meters wide. It's the ultimate archery challenge. It is quite literally like trying to shoot a tiny bullseye on the ground while riding a galloping horse at top speed. And let's say your aim is absolutely flawless. You still have to deal with the fatal flaw of using light. Unlike radio waves, which can punch right through most weather, a simple fluffy white cloud will completely block a laser signal, dead in its tracks. And even on a beautifully clear, sunny day, Earth's atmosphere naturally bends and distorts the light beam. You know how stars twinkle in the night sky? Yeah, that's atmospheric distortion. That exact same effect totally messes with our space lasers. So, how on Earth do we catch a twinkling laser beam that gets blocked by a cloud? Section 5, the solution from astronomy. This is where I love how science comes together. Astronomers have literally spent decades pulling their hair out over atmospheric distortion because it constantly blurs their photos of distant galaxies. To fix it, they invented this incredibly cool adaptive optics technology. It essentially bends the telescope mirrors in real time to cancel out the twinkling and stabilize the image. Well, guess what? A laser beam from a satellite is just light. So the astronomy world already possesses the exact mature technology we need to catch and stabilize those incoming space lasers. And as for the cloud problem, the solution there is surprisingly simple and elegant. You just build multiple receiving telescope stations spread out across a region. Say you want to send data to Seoul, but Seoul is totally overcast today. The system instantly detects those clouds and reroutes the satellite's laser to a backup station in Busan where the skies are clear. Once the laser hits the telescope in Busan, you just pump the data the rest of the way to Seoul using our existing underground fiber optic networks. Boom, problem solved. So what happens when we finally shatter that radio bottleneck? Section 6, the era of space live streaming. The coolest part is, this revolution is already happening right above our heads. Out in the absolute vacuum of space, there's no atmospheric distortion, and there certainly aren't any clouds. Mega constellations like Starlink are actually already using optical lasers to pass data flawlessly between their own satellites. They're passing massive amounts of data at 100 gigabits per second, completely bypassing any ground limits. They're basically weaving an ultra-fast web right there in the stars. And this massive bandwidth is going to completely revolutionize science too. Take something like spectroscopy. Right now, we often just estimate things on Earth using flat photos from space. But spectroscopy breaks down light into thousands of distinct data points to precisely read chemical signatures. With laser broadband, we can instantly download those massive, rich data sets. We could actively and precisely track the specific emissions of greenhouse gases anywhere on the globe in real time, rather than just guessing. To really grasp the tangible impacts coming our way, just look at the applications on the near horizon. In 2026, the Artemis missions are aiming to put humans back on the moon. With moon-to-Earth lasers, you aren't going to be listening to that iconic, scratchy, delayed radio audio like in the Apollo days. We are talking high-resolution, real-time video calls with astronauts walking on the lunar surface. For Earth observation, these massive data pipes mean moving from still photos to continuous live video feeds from orbit. Imagine being able to monitor live port traffic or highway congestion globally to calculate real-time economic GDP. And environmental tracking, a massive upgrade for pinpointing the health of our planet. Making the leap from radio waves to space lasers is exactly like moving from that awful old 56K dial-up modem you used to have straight to the fiber optic internet that lets you stream 4K video today. It changes absolutely everything. So I want to leave you with this provocative thought. When our entire solar system is finally connected by this ultimate broadband network, and we can pull live 4K video from anywhere on our planet or off it, what would you want to watch on a live-streamed Earth? Think about it. Thanks for joining me on The Explainer today, and keep looking up.